Hi everyone, my name is Sergey, and today I will tell you the story of the REST API myth. A couple of words about me before we start. I've been working in this industry, APIs, for more than 15 years right now in cartography and delivery services. Most recently, I joined Bolt, Tallinn, Estonia, as a staff software engineer. I also spent a year and a half on technical architecture group in World Wide Web Consortium. And I wrote a book on API design, which you can find on my GitHub. So I believe I do possess some experience to talk about REST. And let's go. The first thing we need to establish firmly before talking about REST is what is REST. There is some common piece of knowledge that REST was invented or coined by Roy Fielding. This is one of the very much respected authors of various specifications such as HTTP, XML, URI, and so on. And in the year 2000, he wrote a doctoral dissertation. And the chapter 5 of this dissertation called Representational State Transfer, or REST. Most everyone knows this, but I guess not many of you ever read it. Because if you did, you would find that it is actually not what you expected. It contains diagrams like this one on the screen of some distributed software designs, and it enumerates architectural constraints which each software engineer need to be aware of when they design distributed systems. However, more interesting question is what is not there. And what is not there is any recommendations on API design in general, and HTTP API design in particular. There is no such words as REST or RESTful APIs. There is no pieces of advice like put verbs like out of your URLs and all that stuff. It is not a API guide at any extent. What it is about? It simply states and then elaborates over the thought that client-server development in year 2000 is about embracing the client and the server are independent. Clients store some sessions on their side, some cached data, and they operate over a uniform network interface, and the servers are layered, might be a gateway or a proxy, and there is an optional requirement of requesting the code on demand. There are some selected quotations from this dissertation, which I find mostly fascinating, especially the one which is saying that REST is about hypermedia as the agent of the application state, to be discussed in section 5.2. In section 5.2, as you might have guessed, there is no mention of any hypermedia as an application state engine or something like this. Which leads us to the question, so why we are talking about REST APIs as something defined by Fielding or something defined, because there is no definition of REST API. It's not as simple question as it might look. Let me give you some historical overview. I'm not sure this is what you expected from this talk, but it will be fun. So, how it started? From the very beginning of internet, ARPANET, it became obvious that application level APIs are needed, something more abstract than TCP/IP, let's say, or whatever abstraction you prefer. The very first such API found comes from 1969. It's called DEL and defined in RFC 5. And it is, if you read it, pretty much modern protocol. Like if you told me that this is a protocol for some IoT devices to communicate, I wouldn't find anything troubling there. It's about encoded messages and decoded messages. However, this protocol was never implemented, though some protocol in this style, like FTP or SMTP, followed. From the very beginning, the theorists, the scholars were against it because why? Because they were creating software using high-level languages such as COBOL or Fortran or early C. And in these languages, it's quite inconvenient to work with network messages. You need the encoder, decoder, you need interpreting them from imperative code, which is inconvenient. It was quite obvious, again, from the very beginning. In 1966, already it was stated that the user-server distinction must be eliminated entirely from the API design. However, the official birth of the arrival concept happened in 1981. Bruce Nelson proposed the concept he named remote procedure call, and himself implemented one of the first RPCs, Sun RPC, 3 years later. And in this approach, in his book called Remote Procedure Call, Nelson stated that distributed programs should look and behave exactly like they don't contain any network interaction. Here I have the example of the early code working with Sun RPC. The highlighted part is actually making a call. As you could attest, there is nothing like network connection or network errors or something. It is indeed just a call to a local procedure. The idea proved to be, well, at least very attractive. And starting from late 80s and well into 90s, the various RPC approaches became the dominant force. Corba introduced in 1991, then Java RMI. All of them were very nice from a high-level developer's point of view. It provided a very convenient framework to write code. It looked very solid, very enterprisey. The downside was total absence of any concept of having something standardized, interoperable, and so on. Let's say Java RMI simply required both client and server running a Java state machine. Corba declared interoperability, but they actually reached it in 5 years after creating the second version, and so on. However, this was the default approach in the 90s until what happened, the dot-com era. And the outbreak of new services, internet services, which generated huge profits, changed the landscape quite significantly. First of all, you cannot dictate customers what they use, which platforms, in which programming language is written. They were all communicating through HTTP. Secondly, it was not a enterprise environment. You had lots of users generating lots of requests, which are mostly free to them, but they're not free for you. To serve all this massive parallel audience, you need to invent something. And caching, horizontal scaling, and so on became the must-haves. And here suddenly we find that the dot-com services era started resembling something plotted by Fielding in his diagram. It was indeed user agent communicating through HTTP. These requests were split depending on what the content type served. It might be some CDN, it might be file system. And if it lands into an application server, it might be a proxy or a gateway with its own caching, and so on and so on. Could you organize such a scheme with, let's say, Corba? Yes, you can. Furthermore, when I joined one of my previous workplaces in 2008, it was exactly the case. The external call came through HTTP, then been split and converted into series of calls to Corba services, which returned XML, and this XML was aggregated and returned back. Yes, it works, but it is quite inconvenient, as you could imagine. When we started using XSLT to generate JavaScript code from XML, it became completely bizarre and, of course, very challenging to use. What's the obvious solution to this problem? Just simply use HTTP everywhere, right? Why not? Because it allows you to solve all these problems quite gracefully. You have your metadata readable, which allows you to route requests to different types of application service, split them, aggregate them, and so on. And because of this metadata readability, you got a lot of tools working out of the box, which can like help you building such software, like collect metrics, build dashboards, show you nice graphs, and so on. So this is what Fielding summarized in his dissertations, that cost-effective service as of .com era is a layered system, and it would be very nice if this layered system was built on top of one protocol. If you formulate the ultimate commandment of Rastafarianism, it's very simple. You better design your APIs so that any participant could understand what's going on there. That's REST. Quite logically, this entailed using like self-descriptive data formats as well. In REST, you typically rely on text formats such as JSON and XML because they're readable, just like HTTP metadata itself. One thing which Fielding added to this, well, common knowledge is the S constraint, stateless. Fielding stipulated that to use the HTTP capabilities, it would be nice if your HTTP request already contained all the data to process the request. Let me illustrate this principle. Imagine we have something very generic, like a service which creates orders for users. So we have endpoint called post orders, which create an order and returns like its identifier. The question, how would you organize retrieving the order back? Imagine that the client somehow lost the order, the device or like something. Well, you can do it quite generically. Introduce an endpoint called getMyCurrentOrder, which will identify user, then find all orders by this user, and then return the current order back. Will it work? Yes, but it introduces some complexity. Like your backend, which retrieves orders, must know how to identify user, must know how to find orders by user ID, which is like a fine concept if you have one monolith, but became more and more inconvenient once you've got specialized backends. It would be much more convenient if the backend was simply checking whether the exposed order ID belongs to the requested user ID without having index by users, without retrieving orders by user ID. This is the stateless constant. That's a sort of, we can call it proto-microservices. Make backend do their jobs instead of knowing everything about anyone. And so this concept formalized, like being described precisely by Roy Fielding, was an instant success in the late 90s because it provided native support for web services, it provided a lot of ready-to-use tools, It was convenient to build architectures, and everyone loved it. However, its success was hugely disregard to what Fielding actually wrote. It became some sort of new interpretation of his dissertation. And the downside of this popularity became the problem of the technology. Because of low entry barrier, a lot of very complex HTTP specifications and so on, it resulted into a very fragmented and sometimes poorly written code base. And then what happened? RPC returned, starting from the 2009 or something. We've got a whole new generation of the RPCs exploiting all the same Nelson's idea of taking of making network calls look indistinguishable from regular async calls in your code, but embrace all the good parts which were in REST. Which is quite untypical, because if you remember the code I showed in Sun RPC, there was no such things as communication design in early RPCs. You were designing just regular local signature calls. Modern RPC is quite opposite. It is relying on interoperable protocols, most importantly HTTP2 and HTTP3. It is contract first. You first draft your network communication. It provides uniform interface across all the participants of communication. It provides either built-in or third-party gateway software. And of course, it comes with extensive toolings with dashboards, metrics, code generation, and so on. So if you ask a question, what's the difference between RPC, modern RPC2, and second generation, and modern REST, it is actually quite modest. In REST, you address the resource. In RPC, you address the endpoint. That's sort of like a theoretical difference. And in REST, your metadata is fully readable to any interim agent, while in modern RPC, they are not exposing the semantics of the operation at the HTTP level. So only, let's say, gRPC or GraphQL powered middleware could understand what's the meaning of the operation. So if you ask me how to develop REST APIs in 2024, you're asking the wrong question. The right question is, why would you develop a REST API in 2024? Because, as I mentioned on the previous slide, it's more or less the same with the modern RPCs. And the reasons are, first of all, it's full self-descriptiveness. Unlike, let's say, gRPC, when you can't read the data unless you have a proto file, all REST communication is fully transparent. You can get a very good understanding of what happens here, even if you don't have the slightest idea. Second approach is the huge outreach, because it employs just HTTP, no additional layers of complexity. Every device, every platform has a lib for working HTTP. And more importantly, every software engineer knows something how to work with HTTP. And the third advantage you got is a number of built-in tools which allow you to embrace this power of readability. Here on the screen is one of the most famous stacks called ELK, Elastic Log Stash, and Kibana, which allows you to build dashboards based on the HTTP data saved, metadata saved in the logs. So the rules of designing modern REST API are very simple. You do it for readability. All other stuff, like verbs in URLs or nouns in URLs, trailing slash, no trailing slash, is much less important. You're doing it for readability, so make it readable. What this means, make it readable? First of all, you design nice URLs. Second, you explicitly version your things, and you follow the standards, so everyone could read it in the same way you do. Second most important rule, like RPCs, solve specific task. You should address it when you design HTTP APIs as well, which includes like embrace all the advantages of the modern HTTP stack, which is using HTTP 2 and 3, contract first approach, I mean exposing specifications and clients code generated upon the specifications, and of course use all the tooling provided by the ecosystem. And the last slide is quite simple. Why REST in 2024? Because it's explicit, and explicit is always more sustainable than implicit. That's it. Thank you for your attention. If you have any questions, here is my email.